we will learn about beating in phenomena in structural dynamics. This beating phenomena is nothing but when we have the frequencies of external frequency and natural frequency are very close to each other. It's not exactly same, but it's very close to each other. In structural dynamics, the response of a system to harmonic excitation plays a critical role in understanding vibration behavior. Particularly interesting and important phenomena occurs when the excitation frequency approaches near the natural frequency of the system. That means, like, say, this is the external frequency and this is the natural frequency of the structure. If this external frequency is approaching towards natural frequency, then this beating phenomena occurs. Results in oscillation with slowly varying amplitude envelope. This report presents the theoretical background and mathematical derivation and physical interpretation of beating phenomena in single area of freedom. Undamped system subject to harmonic excitation. We consider a single area of freedom system with a mass m, stiffness, and no damping. The equation of motion under harmonic forcing is this one. And dividing through m, we can define the natural circular frequency. That becomes this one, omega n squared. The general solution for this with the zero initial conditions means general solution, the second order differential equation with the zero initial condition becomes this one, f naught into m omega n squared minus omega sine omega t sine omega n t. Using trigonometric identity, we can get the values of this one, like cos omega n t sine omega n minus omega n t. See, for example, if omega is 10 radians per second squared, this omega n also, if it is 11, and if you see these two, it comes around 10.5. Frequency is very high. That means this portion, this cos omega n, and this portion of the equation is a very high frequency, whereas it compares to the sine term. 10 minus 11 means 1 only. 1 by 2 is 0.5. That means it's a very low frequency. Sine term becomes low frequency, low wave, and this is fast wave. So there are two waves multiplied. One is fast wave, another one is a slower wave. So this is the amplitude. Epsilon is the omega n minus omega by 2. That we can say sine epsilon t. We can write the responses. Sine epsilon t, that is this one, and average frequency is this one, and a is the amplitude. Average frequency is nothing but omega plus omega n by 2. Epsilon is the omega n minus omega by 2. This is small when omega is less than or equal to omega n. It's almost equal to, okay, right? So beating phenomena, the system exhibits a beat pattern when the forcing frequency is close to the natural frequency. The displacement of response is a product of fast oscillation and slow modulation envelope. Slow modulation envelope is given by sine epsilon t. Fast oscillation is given by average frequency. This creates a beating pattern. Periodic increase and decrease in amplitude over time. You can see the beating pattern on example also, how it looks like the beating displacement. That is on VBA program. With that we can create this beating pattern. Yeah, this is the beating pattern. You can see how the displacement varies. Here you see this displacement patterns, how it varies. It varies like this. This is the fast frequency, that is a cosine wave, and this you see this envelope, that is a slow wave. It's a slow wave, but amplitude grows a lot. This is a fast wave with amplitude grows a lot. The time and displacement curve is given for this beating pattern. So beat frequency of beat is omega n and half the difference between the frequencies. Beat frequency corresponds to the rate at which amplitude envelope oscillates. Physical significance. Beating illustrates the interference between two slow, closely spaced frequencies. It may lead to undesirable large amplitude oscillations despite moderate excitation. This is particularly important in resonance avoidance, where structures must be designed to prevent natural excitation frequency from aligning. So we will discuss more about this one, group discussion with Professor. Today we will talk about something that looks like simple, but it's not. It's called a beating phenomena. It happens in vibrating system. It can be dangerous if ignored. The trainees look curious. Some start taking notes. Okay, let's start with the basic system. Think of a mass hanging from a spring. It can move up and down. This is called singularity of freedom. That's we know. So it has a spring mass diagram on the whiteboard. Now imagine someone pushes this mass back and forth, not randomly, but with a smooth, repetitive way. That's called with a sine, like a sine wave. That's called harmonic forcing. This is the force, looks like this. F naught is the amplitude of that force. Omega is the forcing frequency. Does the system always move at that frequency? Does the system always move at this frequency? No. It depends on something else too. Right? This mass and spring have a natural frequency. That's a frequency at which the system prefers to vibrate. We call it omega n. So actually the system prefers to vibrate at this frequency, natural frequency, but the external force is trying to make the system to vibrate at this forcing frequency. And that's where this is the resistance part, this is the driving part. That's where the balance we need to find it out. Now comes the interesting part. If the forcing frequency is far from natural frequency, the system responds steadily. But when it gets close to omega, something unusual happens. Is that where beating starts? Exactly. When the omega is almost equal to omega, the system starts to beat. See, it draws two waves, one with fast oscillation and one with slow oscillation. This is the slow oscillation variation. Another one is the fast variation. This looks like this. So beating is when the motion of the system grows and shrinks again. The system shakes first, but the size of the shaking changes slowly. It goes up, then down and up again. Why does that happen? It's because two waves are interfering. One wave comes from the forcing, and the other is the system's natural motion. These two waves combine. Sometimes they add up, sometimes they cancel out. So this is because of sometimes they add up and sometimes they cancel out. The math behind it, let's look at the math. Don't worry, I will keep it simple. The solution for the displacement of the system starts from the rest is, this is a solution. And now when we apply the formula from trigonometry, sine A minus sine B, that is this portion, equal to 2 into cos A plus B by 2 cos sine A minus B by 2. When we have these two functions, sine omega t minus sine omega n t, in this trigonometric formula, it becomes cos multiplied by sine. Using this equation becomes, beating is not just a theory, it's a real danger. It can cause large motions even if the force is small. The shaking gets worse over time. This can cause cracks. Can we prevent it? We can avoid the forcing frequency structure at this natural frequency. We can also use dampers. Damping also reduces the motion. We also design structures to shift the natural frequencies. Omega is the forcing frequency, omega is the natural frequency. Beating is amplitude grows and shrinks. So x of t equal to a into cos omega plus omega 2 by t sine into omega minus omega by t. What do these two terms mean exactly? Why are there two different frequencies? One frequency is omega n, another one is omega. Why are there two different frequencies? Excellent question. This equation tells us how the system moves over time when it's being forced at a frequency close to its own natural frequency. Let's look at each part step by step. So this cosine term, first the amplitude A depends on how strong the forcing is and how close omega is to omega n. But the real magic happens in these two terms, cos omega plus omega n by 2 t, right? This is a fast vibration. It changes quickly. It acts like a carrier wave. It's what you see when you zoom in close. When you zoom in close, this is what you will see. It represents how the structure wants to shake, somewhere between its natural frequency and forcing frequency. So it's like the structure reacting quickly. Yes, this means the vibration you feel. This is the main vibration you feel when you touch the structure. This is the main vibration you feel when you structure. It's the high frequency part. Next one is sine omega minus omega n by 2. This is very small, slow part because frequency is very less, right? The difference you are taking on half of the difference. It changes much more gradually. It controls the overall amplitude. So overall amplitude is controlled by this term. How big the vibration gets. This is what we call beat envelope. So it's not shaking slowly. In the size also grows. It's a size that's changing slowly. The structure is always vibrating fast, but how big those vibrations are that grows and shrinks slowly, that's the beating. You can think of it like a wave riding on another wave. Imagine you are in a car with the two fans running. One fan spins at 1000 rpm, another 1005 rpm. Individually they sound smooth, but when they are both running, you hear soft sound. That's a beating. The sound grows and fades because they are close but not exactly the same. That's what happens in the formula. The structure has one frequency, the force has another. They are almost equal. The tiny difference is what causes the amplitude to grow and shrink. How often does it beat? How long does it take for one full beat? That depends on how close. The close they are, the slower the beating. The beat frequency is difference, half the difference between these two, right? This tells us how many times per second the amplitude cycles from low to high and back again. So if the forcing frequency is very close to natural frequency, that beat is slow. That's dangerous because the structure stays in that high amplitude state for longer. It may even hit resonance if you are not careful. Why this equation matters? It helps engineers in life. If we know the frequencies involved, we can predict how the structure will respond. We can design dynamic system. We can shift the natural frequency, and we can change the excitation source. So analyze the beat equation again in circles. This small term is quite sinusoid. It is the one that often gets ignored, but it's the one that tells us something big is coming. See, it turns to the trains these two parts. Look at carefully at this equation. It tells us how the system moves over time. The displacement x is where the mass is at any point of time. See point of the cosine term. See this first part. This is the fast vibration. It changes quickly with time. And what do you mean by fast vibration? This term causes the system to shake rapidly. The frequency is about halfway between. So it's close to both frequencies. Now look at this part. This term changes much slower. Why is it slower? Because it depends on the difference between these two. Why it is slower? Because it's the difference between these two. Half the difference between these two, right? Usually this difference is very small. When you divide a small number by 2, multiply it by time, the change is slow. This is a slow sine wave on the board. The slow sine wave controls the size of the vibration. It makes amplitude to go up and down slowly. So the system shakes fast but gets louder and softer slowly. Yeah, here you can see exactly the system is always quickly moving quickly. How big it's shaking, grows and shrinks slowly. See here, if you see, this is the fast vibration part. This is the cosine part. It slowly, the fast vibration is happening, but slowly it grows. After that it fades away. Then it grows in the other direction. Then comes to this original. So this is how this frequency is going up, after then slowing, then going up, then slowing, going up, then slowing, like a beating happens. This is the slower portion, is this one sine part. You see, this takes long time to complete one cycle, but the fast vibration, you see, this fast vibration means this takes very small to complete one cycle, right? This is the fast vibration. This is the slow vibration. Slow vibration is sine wave. That frequency difference is there, omega minus omega n by 2. That's less frequency, low frequency. But this is high frequency, omega n plus omega n by 2. This is the difference, this is the addition. So the wave sometimes adding up, sometimes cancelling up. That's why this beat is happening. Why two terms? This equation is a product of two sine waves combined. When two waves close with close frequency means they create this pattern. One part vibrates fast, other changes size. Can you give an example? Think of two guitar strings. One tuned the frequency, another one tuned slightly off a tiny amount. See plugs in imaginary string. When both strings sound together, you hear the pulsing sound. Sometimes the sound is loud, sometimes soft. That's the same as amplitude going up and down. Pulsing is the beat envelope. The loudness is the amplitude from the sine term. Fast vibration pitch you hear from the cosine term. What happens if frequencies are close? If omega is very close to omega and the difference is very small, this makes the sine term change slowly. It's almost equal to 0. If sine term is 0, this means amplitude stays high for a long time. The system shakes strongly for longer. Is that bad? It can be. This is the dangerous part of beating. Long periods of high vibration can cause damage. What happens if frequencies are not close? If it is omega is far from omega and the difference is large, the sine term changes quickly, so amplitude changes fast too. But this fast change means vibration won't stay strong for long, it goes up and down quickly. The rate at which the amplitude change is called beat frequency. So the rate at which amplitude is changing at a beat frequency. Beat frequency is very less value. Beat frequency is slow. That means amplitude stays long for time because amplitude is not changing quickly. If it is not changing quickly, the high vibration, if it is large vibration happens for a long time, it's going to damage the structure. And this tells us how many times per second amplitude grows or sinks. When we are closer, f beat is smaller. Exactly smaller, the f beat means slower beating. Why do we care? Beating can cause stress to the structure. When the amplitude is high for a long time, parts get tired, shaking our small object violently. Imagine shaking a bridge or machine parts like this over time, they can break. So we want to avoid forcing near natural frequency, or we design to reduce the beating effects. We are damping or change frequencies. Cosine term fast vibration, sine term controls how the amplitude changes slowly. Amplitude grows and shrinks in a beat pattern. Beat frequency depends on how close the forcing and natural frequencies are. When frequencies are close, beating is slow, amplitude stays high for longer. Long-lasting high amplitude can damage structures. Why are the two parts multiplying each other? What does each one mean? Looks at one of them. What do you think the cosine part might represent? Maybe quick movement. Exactly. Cosine term. It's a fast vibration. System is shaking quickly back and forth. Or the sine part looks different. It changes much more slowly. Can you guess why this slow change? What this slow change might control? Could be the size of the shaking. That's called beat envelope. It controls how big or small vibrations over time. The system is always shaking fast, but how hard it shakes up goes on down slowly. Think of it as a fast pulse wrapped inside a slow wave. But why does the sine part change slowly? Because it depends on the difference between the two frequencies. When they are close, the difference is very small, so the change changes very slowly. Why does a small difference make it slow? Because the argument of the sine is tiny. Sine wave value moves very slowly as time passes. What if they are exactly same? What would happen? If they are same, difference is 0. The sine term becomes 0 for all time. This formula does not quite apply. Instead, the system goes into resonance. The amplitude can grow without bound unless there's a damping. Can you give a real world example to imagine this better? Sure. Imagine two guitars. One plays a note of frequency, the other is a tiny bit of maybe what do you hear when both play together? A pulsing sound. The pulsing sound is a beat. Fast tone is from the cosine term and pulsing loudness from the sine term. How do you calculate how fast the pulsing happens? And that's called the beat frequency. The smaller the difference, slower the beat. So if the frequencies are very close, the system vibrates strongly for a long time. If frequencies are close, beat frequency is less, and the system vibrates for a long time. This can be dangerous because structure stays in high vibration state longer, which might cause damage. Can you stop beating from happening? We can try. One way is to avoid forcing at frequencies close to natural frequency. Another is to add damping to reduce vibration. How do you know which part is the fast vibration, which was slow? What tells us what? What tells us that? It all comes down to the numbers inside the cosine and sine. This is roughly the average of two frequencies. Since both frequencies are smaller, similar and quite large, this term is big. Now this one is the difference between the frequencies. If the frequencies are close, the difference is very small. Bigger number inside cosine equal to fast changes, smaller number inside is slow changes. So cosine term oscillates quickly because its frequency is high, and sine term oscillates slowly because its frequency is low. Exactly, but why do we multiply these two terms instead of adding? Multiplying these two sine elements is what creates beat effect. It's a result of a trigonometric identity called the product to some formula. Can you show how the multiplication creates this beat pattern? Cos A sin B can be written as the sum of sine and cosine waves with different frequencies. The interaction makes the amplitude modulator, that's B. What if the forcing frequency is much different from omega? What happens then? Omega are far apart, the difference is big. That means sine term changes rapidly. The amplitude oscillates fast, so the system never stays at high state for long. The beat effect is weak and less noticeable. So beating is strongest only when they are very close. The closer frequencies are more noticeable the beating. Can the amplitude get bigger? When the sine term reaches its peak, the total displacement can be twice. What happens if the system has damping? Will the beat still happen? Will the beating still happen? Another damping reduces the amplitude over time, but it smooths out the peaks, making amplitude changes less sharp. Beating still happens, but vibrations don't grow as large as long or lost as long. Is this why engineers dampers to the building spaces? Dampers reduce the risk caused by resonance and beating. Can we see beating in everyday life besides music? Think about two nearby car engines running slightly off sync. Sometimes you hear a pulsing hum or old radio signals that sound like wah, wah. Those are also beats. How can we use these frequencies understanding to protect structures? We use to design systems carefully. We avoid frequencies close to natural ones or are damping. Sometimes we change the structure's difference most to shift natural frequency. So this simple equation helps prevent real damage. It's a simple but powerful. It tells us what to watch out for. Can you give us an example? Okay. What exactly does A stand for? Is it fixed or does it change? Is it fixed or does it change? A is amplitude constant. It depends on the force strength, system's properties. The important part is the sine term changes the effective amplitude over time. Does the sign of the sine term matter? Can it be negative? Sine term swings between plus and minus. When it's positive, amplitude adds up. When it's negative, it subtracts. This causes the vibration to get louder and softer, like pulsing. What if the difference is zero? The system stops moving? The formula doesn't apply exactly because the sine term becomes zero. Instead, resonance happens, amplitude grows continuously, limited only by damping. Just an extreme form of beating. You can think of it like that. Beating happens near resonance, but when slight different frequencies. Resonance when frequencies are exactly equal. How does the damping change the shape of this equation? Damping adds an exponential decay. So instead of amplitude growing or pulsing forever, it gradually fades out. So in reality, beating won't go forever. In real structures, damping prevents infinite vibrations, but the beating can still cause large stresses before it dies down. Beating can still cause larger before it dies down. Beating happens in systems with more than one natural frequency. Real systems have many natural frequencies called modes. Beating can happen between forcing on any of these modes. Can two different modes beat against each other? Two modes have close frequencies, both are excited, the interaction can cause complex beating patterns. Is beating only a problem mechanical? No, it depends on electrical circuits, acoustics, even in optics, where waves interfere. How do engineers measure these frequencies in real life? By using sensors like accelerometers, analyzing vibration data, finding natural frequencies by exiting the structure and recording its response. Can we predict the beating before building something? Yes, engineers use computer models to calculate natural frequencies and simulate response. Why don't we just avoid all frequencies near natural ones? Sometimes it's impossible because the forcing might come from environment or operation. Then we use damping or change the structure of the design. What about the tuning the system? Like in machines, we tune or shift natural frequencies away from the known excitations to avoid beating. Can you show how the wave looks on graph pictures? That must feel like the system suddenly stops shaking. Beating is just about the amplitude grows again. Is this like two waves cancelling and reinforcing each other? That's the essence of the beating. Interference of close frequency waves.